Hello, everybody, and welcome to F8. Okay. So this afternoon's track here in the blue room is the Hack Away track. So this is a little bit different to what you heard this morning, a little different to what's happening in some of the other tracks, but we hope this session is going to give you a little bit of insight into what we do at Facebook ourselves to build our own apps and to launch them to the world. So one of the things I love about Facebook engineering and the teams here is that they love to tell stories. Stories about our culture, how we like to move fast and break things or ship stable infrastructure, and how we ship love to our users around the world. We also like to tell stories about the challenges that we constantly face as an organization, as a company. We like to talk about those challenges brought on by moving at the speed we move and at the scale of our business. But more importantly, we like to talk about the solutions that we've come up with to those challenges, whether they be innovative ideas, software libraries, tools, processes. And we like to talk about how we then go on and share those with the world through our open source program and through forums like this one. So I'm thrilled to introduce the session this afternoon. The track is going to take us on a journey. It's going to talk about many, many aspects of our engineering business. We're going to start off talking about some of our web infrastructure, both on the front and on the back end. Then we're going to spin across to mobile, and you're going to hear from the team that built our Messenger app, one of our primary standalone Facebook apps. You're going to hear from the Paper team about how they built their new iOS app. We're going to hear from the Android team, who are shipping high-quality products to hundreds of thousands, hundreds of millions of users. And you're going to hear from our release team, whose responsibility it is to get all of that out into the app stores and out into the hands of our users. So my name's James, but I only have one job today, and that is to get off the stage as quickly as possible and make room for the teams that are going to take you on this journey. So without further ado, I'd like to introduce from our front-end web infrastructure team, Jing, Pete, and to kick us all off, Tom.
Awesome. Great. James, thank you so much for that introduction. Everybody hear me over there in the soft seating? All good? It's worth noting, all this seating, this actually came from our office. We shipped it all in so that we could, make this space as comfortable as possible. I think we have the best room in the house here. Certainly the most comfortable in my opinion. So welcome. I'm Tom Okino, and I manage the JavaScript infrastructure team at Facebook. One more. So I work on a bunch of stuff. I've worked on a bunch of stuff over the years. I still write code whenever I can, even as a manager. And over the years, I've built a lot of different things. I've worked on a lot of different projects. But one of the things that I've tried to do over the years, the thing that holds everything together, the thing that kind of ties everything that I've worked on together, is I was always trying to build quality software. And this is what we're all trying to do, right? We're trying to do this at Facebook. All of you, if you have startups or you work at companies, you're trying to build high-quality software. So let's talk for a minute about what quality software actually means, right? There's a few important pieces here. The most important piece is whatever you're building, if it's an app or a feature or a product or whatever it is, it needs to add value. It needs to really add value to someone's life. It needs to be useful and provide utility. If you don't provide utility and you don't add value to someone's life, then the rest of this doesn't matter. We don't even need to talk about it. But once you have a good idea and you produce something that adds value to someone's life, there's a couple other things we need to focus on. For our software to be quality, we need it to be reliable. We need it to be high performance. The user experience has to be great. We also need it to be enjoyable and easy to use. Does it make sense to everybody? Kind of agree? Has to be good. The thing is that quality takes time. And in fact, the higher quality you want your application or your product to be, the more time you kind of have to put into it. Does that resonate with anyone? But one of Facebook's core values, and one of the things that we value the most, is our ability to move fast. This is really important to us. We need to be able to go from an idea that an engineer or somebody has to in production, in people's hands, as quickly as we possibly can. And then once it's in production, we need to collect feedback and metrics and data, and we need to iterate on that thing as fast as we possibly can so that we can get to the best possible product. Now, it seems like these two things are at odds with each other. On the one hand, we want to produce something that's really high quality, and we know that's going to take some time. But on the other hand, we know that we need to be able to move fast and get to market as quickly as we possibly can, or else somebody else will do it before us. Is there a way that we can produce higher quality software in less time? Well, we can try a bunch of different things. We can try cutting features from whatever we were building, right? We can try saying, oh, you know what, this feature, we don't have time to build it. We need the rest of this experience to be high quality. We're just going to cut it. Well, listen, a minute ago we were talking about adding value. If we were trying to build a minimum viable product, cutting features isn't an option. You no longer are adding the value that you were trying to seek out to aim to build. So what about adding engineers? Can we just add as many engineers to this as possible, get it done super quick? Well, anybody who knows anything about the mythical man month knows that you can't just throw more engineers at this problem. You can't just add people to the project and expect that it's going to get done really quickly and super high quality. What about just asking all of our existing engineers to work harder? All right, everybody, for the next 3 months, we're going to work for 80 hours a week. Cool? Right? That's obviously not sustainable. What we really want to do here is we want to change the math on this. We want to make it so that we produce higher quality software and better code by default. And we want to do it in less time. So we've experimented with a bunch of different ways to do this, especially on web. I'll talk about one of those things. We tried MVC. We tried this a lot of places on the web. And what we found is that in our sufficiently large code base, in our sufficiently large organization, MVC got really complicated really quickly. Now, Jing is going to talk more about this in a few minutes, but I want to describe what actually happened. Every time that we tried to add a new feature to one of these systems, the complexity of the entire system just blew up, right? It wasn't just the new feature that added a little bit of weight to our code base, but everything kind of got more complicated. What was going on is the code was responsible for doing more things, and the data was used in more places, so our code got really unpredictable. And what I mean by unpredictable is that a new engineer coming into our code base, looking at code for the first time, would have a hard time getting up to speed. They'd have some task that they're trying to complete, and it would take them a long time to kind of actually be able to be productive in that code base because they didn't necessarily trust what was going on. They couldn't make changes to that code easily because they were afraid of what was going to happen. So, they have the one engineer who actually built this thing, and they go to that person and they say, hey, I need to make some changes here, right? If you have one engineer who is the only person willing to touch an area of your code base, that code might be a little bit unpredictable. Has anybody ever experienced that? Like one person, yeah, right? There's only one person that'll make that change. So this became really, really hard for us. We were moving really slow because our code was fragile and unpredictable. So for us, at least, MVC kind of fell apart. What we thought is that if we can increase the predictability of our code base, we can make it so that new engineer coming in can get up to speed really quickly and make changes more confidently, okay? We thought we'd be able to produce higher quality applications in less time by just making our code, just structuring our code a little bit differently in a way that makes it more predictable. Okay, so this is what we're going to be talking about today. We're going to be talking about two systems, an architecture and then a framework. FLUX is a system architecture that encourages single directional data flow through your application. And Jing is going to come up and talk about that in a minute. React is a framework that allows you to build user interfaces in a way that is a lot more predictable, a lot more declarative, and we think a lot more powerful. And at least anecdotally speaking, React has allowed us to move a lot faster internally at Facebook. And now we're seeing that same success throughout the internet since we open sourced this last year and released it back in May of last year. So with that, I'm going to invite Jing up to tell us a little bit about the first system for managing our data called FLUX.
Great. All right, thanks, Tom. So my name is Jing, and I'm a software engineer on the product infrastructure team at Facebook. So let's talk about some of the problems behind MVC that make it not scale, and how FLUX proposes to solve some of those problems. Well, MVC works pretty well for small applications. Everything has its own particular role to play. The problem is that it doesn't make room for new features. Let's look at what happens to this diagram when we add a lot of models and when we add a lot of views to the system. There's just an explosion of arrows. And if you just look at these arrows, can you tell if there's an infinite loop here where the model triggers something in the view and the view triggers something in a different model, and it goes in a cycle? It's really hard to tell just by looking at this. And that's with all of your relationships drawn out. If you were to look at that in code and try to figure out, where do I have an infinite loop somewhere in here that's causing my app to just go in constant loops, it's really difficult. I was drawing a very similar diagram while I was trying to figure out the architecture of one of our more complicated interfaces. It looked very much like this. And it was so complicated that I ended up drawing numbers instead of arrows to represent the relationships between them. That's how dense the arrows were getting. So we want to do away with all of this. What we propose instead is something called FLUX. It's a single directional data flow. And that avoids all of the double arrows that go in both directions that make it really hard to understand the system. What we have is an action coming into the system, a dispatcher that sort of acts as the traffic controller for the whole thing, the store, which is the data layer that basically updates whenever you get a new action, and then the views re-render whenever the stores say something has changed. And then from the view side, they can throw another action back into the system. The dispatcher here is the main piece that enforces that there's no cascading effects. Once an action goes into the store, you can't put another one in until the stores are completely finished processing it. That's pretty abstract, though, so let's work our way back to this, and let's use a real-world example, a chat interface at Facebook. We knew that we had a problem with chat in 2011 when we introduced the subscribe button on our blog, and the first comment on that blog post was, "Please improve chat system," with 898 likes. And this was one of our more polite requests. We got a lot of comments that would just say fix chat, and that became a pretty frequent refrain in all of our user comments. So how do we get to this place? How do we get to the point where we were annoying our users so much they just wanted us to fix chat? They didn't care what else we were launching, they didn't care we were improving, they just wanted us to fix chat. Well, to answer that, we have to go through sort of the chat feature as it evolved. We started with something pretty simple. You have a chat tab, shows a list of messages. Whenever you get a new chat message, you just append it. It's pretty simple. The code is pretty manageable. Later on, we also launched the messages jewel, which shows you the number of threads that have unseen messages on them. That was kind of developed independently from the chat tab. But whenever a new message comes in, we also want to handle that unseen count. So this code gets a little bit more complicated. We have an unseen thread count that we want to bump every time we get a new message. And if we think that the user's looking at it, we also want to decrement it. A couple months later, we also introduced the larger messages view. And with that, we made this handler even more complicated. This is what we had before. And now we have to sort of account for the messages view and decrement the count under the right conditions if we think the user is looking at either one of the views. So what are the problems here? One is that the code really has no structure. It's very imperative. That makes it fragile. And we lose a lot of the original intent behind it. It's hard to tell just by looking at the code that you want to keep the messages view and the chat tab view in sync. It's hard to tell that you only want to increment and then decrement. You don't want to do either of those more than once. And as we add more features, this code just only gets longer. And having something imperative like this basically led us to the situation where we had our most annoying chat bug happen over and over. Users would get an unseen count, and there would be no unseen messages behind it. Everyone's sort of used to seeing one of these numbers, clicking on it, and you get something new behind it. That's exciting, but when they get that number and they click, there's nothing there, they refresh the page and it's gone, that's really annoying. It's really frustrating. And that's what led to the whole fixed chat user feedback. And it wasn't like we didn't fix the problem. We would always fix some particular edge case, but this problem would keep coming back just because the whole system was fragile. And that was a good sign that something was fundamentally wrong here. So how can Flux help with something like this? If we're looking at the structure of the code that we had before, we have sort of the fundamental pieces. We have chat tab, main messages, an unseen counter. And then we have an external handler that goes in and changes some of their state. They each have their own state, but the handler goes and modifies them. Right? All of the logic to modify state based on a new message coming in is in the handler itself. And so those three different pieces no longer have the ability to maintain internal consistency. They basically don't have that information. They've already ceded that control to the handler. What we want to do instead is internalize this control. We want to move all of the control into the individual pieces so that the state is right next to the logic that updates that state. So for chat tab and main messages, it's pretty easy. You just want to append a message whenever you get a new message. But it's a little bit less clear what to do with the unseen counter. We know that you want to still increment whenever you get a new message, but where do you decrement that unseen counter? You don't have enough information at that point. What this structure makes clear is that we need more explicit data. What we really want is to keep track of a list of the unseen threads, not just the unseen count. And then what we can do is whenever a new message comes in, we can add that thread to the list. And then further down the line, we can have the UI decide when to mark that that thread as seen, and it can remove it from the thread list. Having more information this way means that that thread list stays more consistent. If we put in 2 mark seen messages, no harm done. The second one is a no-op because that thread has already been removed. So what we learned here is that we should use more explicit data on the client instead of derived data. In this case, what that means is the unseen threads list is the explicit data, and the unseen count is the derived data, which is the length of that list. And doing it this way gives the client a lot more control and a better ability to stay consistent overall. We also knew that we wanted to separate data from our view state. This isn't too different from MVC. It's very non-controversial, but it does add to our system diagram a little bit. So now we have an action coming in to the messages, threads, and unseen threads state. And whenever those update, they tell the views, hey, something changed and you should go re-render. The biggest difference between Flux and MVC is that we want to avoid cascading effects by preventing nested updates. So what does that mean? Well, if we look at our system, what that means is that we want to let the data layer completely finish processing before we trigger any additional actions. In this case, it means that the actions come in, the messages, threads, and unseen threads stores finish processing that, tell the views to update, and only then can the views say, I want to mark something as seen, and that goes back in through the system. The benefit here is that there are no arrows going in the other direction. More generally, what this diagram looks like is you have an action that comes into the stores update the views, and all of your actions take the same structure. Nothing goes in the other direction. And having all of your actions go through the same flow makes it really easy to onboard a new person. When I was working on the teams that use the system, intuitively I wanted to go and basically sit down with any new person and try to wrap them up quickly, tell them sort of everything they needed to know. But what we found is that this wasn't really needed with a system like this, because what they could do is trace how one action flowed through the entire system and have a pretty good idea of how the rest of the system worked. And that is what really helped us move more quickly. So going back to our original diagram for Flux, we still have the action, the store, and the view. But we also have a dispatcher in here that's the traffic controller of the whole system. What it does is it ensures that until your store layer is completely done, the views or anything else can't put an action through the system. Instead, if it gets an action while the data layer is still processing, it can throw. And it's a good constraint to have. It does seem constraining, but that constraint is a guarantee for all future developers, including yourself. It's a guarantee that if you understand where your action starts and what it changes inside of the data layer, you know all of the downstream effects. It doesn't have anything that propagates and cascades on down that crazy graph with all the arrows. It's single directional, it goes in one direction, and once you finish the single layer, you're done. If we sort of imagine this flux diagram with more stores and more views, it all collapses down to the same thing because all of the arrows go in the same direction. With MVC, you can't sort of form a simple mental model because the arrows go in both directions. But with this, with the arrows going in a single direction, you can collapse it down to exactly this diagram, and that's your mental model for the whole thing. All right, so when we switched over to Flux, in our chat system, what we found is that it improved our data consistency, so that if you look at your chat tab and your messages view, they would always be in sync. It became a lot easier to pinpoint the root of a bug. So when other employees came to us with bug reports and they described what happened to them, we would usually be able to say, hey, I think it's that module. That's the most likely suspect. And that actually helped us move really quickly because instead of trying to trace through a handler and all the downstream effects there, we could just say, it's probably this module. Let me go look at it. And that shortened our iteration cycle. And finally, we were able to write more meaningful unit tests as a result of this. What does that mean? Well, because all of the state and all of the logic that updates the state is in the same place, we basically could test that module by saying, let's assume that you're in state A, we give it an input, and now we can test that it's in the expected state B, and that state B is consistent. A lot of our unit tests look like this, and they were really effective and helped us avoid making the same mistake twice. Okay, so we've looked at a lot of boxes, I made a lot of abstract arguments. What was the real-world impact of this? Well, our most common chat bug, that zombie unseen count that would go away as soon as you clicked on it, we stopped seeing that, finally. If we stopped annoying our users every time they tried to chat, we saw a drastic drop in our user tickets about chat, and most importantly, this bug hasn't been back to haunt us. Like I said before, we would always fix it, but every time we add features, and every time we change the logic behind it, this bug used to come back. Once we changed the underlying system, the underlying architecture, this bug went away for good. All right, so at this point, we're in a pretty good state with our data flow. But our rendering layer was still a little bit difficult. The initial render is pretty easy. We have a list of messages come in from the data layer. That renders into the markup for the list of messages. Still pretty manageable. But whenever we wanted to update it, we didn't want to just re-render the entire thing. We wanted to optimize it a little bit for the new message case, because that happens so frequently, and you might have a really long list of messages, and users might notice, if we start re-rendering every time and the UI flickers. So what we had instead is the rendering layer would look at the messages list that the data layer gave it, and find that it has one more message than previously, and it would translate that into an append operation. The problem with this code is that it became really fragile over time. We had to account for different message types. We had to account for messages coming in out of order. And this code just got more fragile over time. We had one guy on the team who knew it, like Tom said, and nobody else on the team wanted to touch it. Everyone else was willing to jump in on any other bug in the data layer because they were comfortable with it. But intuitively, they knew that this code was fragile, that it was too difficult to change without breaking something else, and they just wanted to defer to the one guy on the team who understood everything. So that's kind of a bad sign. What we really wanted for our rendering system was to be able to always re-render, no matter what. Give it a list of messages, we know how to render that list into the DOM. What we really wanted was a rendering library that would efficiently do that change for us without interrupting the user experience. This is where React comes in, and here's Pete to talk about how React solves this problem.
Hey everybody, I'm Pete and I work on the React team here at Facebook, and I also manage the Instagram web team. So Flux gets your data model into a really predictable state. It's very easy for you to understand what's going to happen in your system. But Jing brought up a really important point, which is we have to render this consistent data model to the user interface, and that's a pretty difficult problem. So difficult, in fact, that we built a user interface library called React designed to solve the hardest problem in this space, which is that data changing over time is the root of all evil. So here's an example piece of user interface from our chat product. It's the buddy list. Now, I'm going to read off a series of mutations to this buddy list, and I'm going to ask you what the state of this should be at the end. So I'm going to ask you what it should look like. So are you ready? You guys have this memorized? All right. I know it's after lunch, but I'm going to assume you guys memorized it. All right, let's go. Ready? So Alice went offline, Bob went offline, Steve went online, Bob went online, Charles is idle, and Charles is on mobile. Now, what does this user interface look like? Does anybody know? I don't know. I have no idea. Because processes that are spread out over time are very difficult for humans to understand and hold in their head. Just these imperative actions that mutate state. It's very difficult for you to figure out what that state is at the end of that sequence of mutations. And I'm not the first person to discover this. Dijkstra has a really great quote about this. He says, we should do our utmost to shorten the conceptual gap between the static program and the dynamic process, so that to make the correspondence between the program and the process as trivial as possible. Now, what Dijkstra is saying here is he's saying we need to take this series of imperative mutations, these things that are changing over time, and try to make it look like a program that executes at a single point in time. So if you go back to that buddy list example I was just talking about, if I presented a consistent snapshot of the data at any point in time, it's very easy for you to visualize what this user interface should actually look like. You can imagine how we would draw this on the screen. So back in the 90s, when we were doing server-rendered apps all the time, we didn't have a lot of JavaScript running on the client. This is actually how we wrote user interfaces. So when the data changed in your application, you simply hit the refresh button in your browser. And what would happen is the browser would go to the server, fetch some data from the database, which would be a consistent snapshot of the state of your application. It would turn it into an HTML page and flush it down to the browser. So what we've done with React is we've taken the mental model of a 90s-era server-rendered web app, and we've brought it to the client. So whenever the data changes, whether it's from Flux or Parse or Firebase or Backbone or whatever you're using to get data on the client, React will conceptually re-render the entire component every single time, just like a 90s-era web app. Now, when I say 90s-era web app, what I really mean is a RESTful web service. So if you're bringing that model to the client, you get a lot of the benefits of RESTful architecture for free. So one of the important parts of RESTful architectures is idempotency, and a similar concept is referential transparency. So when you model your UI as a referentially transparent function, you get a lot of benefits. So think about how the web works today. When you type a URL in, you always get the same resource no matter what. With React, when you put in data, you always get the same user interface rendered at any point in time. And whenever the data changes, you can simply refetch and refresh, just like in the 90s. And so one of the reasons why people use RESTful architecture so much is because they're so predictable. It's very easy to cache them. You understand the performance characteristics and how to scale them out, simply because for the same set of inputs, you get the same set of outputs. And a lot of great stuff falls out of this, like testability. A lot of our unit tests for our user interfaces at Facebook started out as, click on this button, mutate this state, a series of imperative actions, and then we would make some assertions along the way. Since we've adopted this model, we do a lot less of that and a lot more of sending in a consistent state and making some assertions on what was actually rendered based on that state. Now, this sounds like a pretty great model for building applications, but we can't do this with the regular browser APIs we have today. And the reason for that is that the DOM is stateful. So if we were to re-render all of the DOM nodes whenever anything changed in our application, we would have a really poor performance profile and really bad user experience. The browser was not designed to be constantly creating and throwing out DOM nodes. And additionally, if somebody's typing into a text field or has an inertial scroll going on, if we were to throw out those DOM nodes and recreate them, we would kill that scroll momentum and scroll position, and it would just be a really bad user experience. And this actually isn't limited to the browser. This is any stateful UI toolkit. So imagine implementing this on iOS and UIKit. People generally don't destroy and recreate view hierarchies on every change because of the performance characteristics and because of the user experience problems. So what we did at Facebook is we spent the past couple of years building what we like to call a virtual DOM abstraction, which is implemented in this library called React. And what the virtual DOM lets us do is it lets us model our UI in the way that I just described, conceptually re-rendering everything and in an inexpensive and good way for user experience. So here's how it works. whenever the data changes, we re-render your application to the virtual DOM, and we create a new tree of virtual DOM nodes. Then we diff that new tree of virtual DOM nodes with the previous tree, the one that existed before the data changed. Then we can isolate what were the changes between the two virtual DOM trees, and we can compute the minimal set of DOM mutations necessary to make the real DOM look like the virtual DOM. We put that into a queue, and we flush that queue to update the UI. So here's an example of how that works. Remember the buddy list example. We have the initial state that I showed you in this screenshot on the left, and we have the state that we want to get to after all those mutations on the right. Now again, we can't just throw out the DOM nodes and re-render them for the performance and user experience reasons I just mentioned. So we have a virtual DOM diffing algorithm that goes through and highlights what actually changed in these two data structures. So I've colored those changes in yellow. And what the system will do is it'll eventually turn it into imperative DOM mutations, just like people write on the web today. Now, remember, this is actually the most difficult part of the engineering of the UI, these imperative mutations that change over time. If you think back to that buddy list example, this is the same thing. This is just the code representation of those mutations. But the key here is we push the complexity of those mutations into the framework. So the end user of the library doesn't even need to think about it. So they think about how their UI looks like at any point in time as a complete snapshot, and the system figures out the imperative mutations needed to update the UI to make it look correct. So if you've been following so far, this might not seem like a very performant system, because we're re-rendering our UI all the time to this virtual representation, and we're diffing a lot of things that may not have actually changed. In this example, only 2 pieces of data changed out of that whole DOM structure. The good news is, this is how high-performance 3D games work. So one of my colleagues built a game a couple years ago called Doom 3, and here's how it works. We have the game state that represents the consistent state of the world. So we have user input events that come in and mutate that state, and we have network events that come in from the game server. And that world state goes into the front end of the game. Now, the front end of the game represents all the rules of the world, so how players move around, how weapons work, that type of thing. And out of that component comes what we like to call a scene intermediate representation, which is a logical, declarative description of what needs to actually be drawn. Now, they take that logical description of what needs to be drawn, and they put it into the back end, which turns it into OpenGL operations that are imperative and go over the bus to the graphics card. Now, the architecture we came up with for React in this virtual DOM abstraction is very similar. We have your application state, which is updated by server events and by browser events. That goes into your React component, written in JavaScript, which describes the business logic of your application, the rules of your app. And then that generates a virtual DOM representation rather than a logical representation of a 3D world. We pass that virtual DOM representation into the back end, which then computes imperative DOM operations rather than OpenGL operations and renders them to a browser rather than a graphics card. So I think that this is pretty cool technology. But Facebook doesn't build technology for the sake of technology. It has to have impact. It has to make our developers and our users' lives better. Now, Tom touched on this earlier. Our whole goal with all of this is to improve quality for the same amount of engineering time. So we have to basically move faster without breaking things. And we identified that focusing on making your code predictable is a really, really great way to improve these two things. And the two systems that we've come up with are FLUX and React for making your data layer and your UI more predictable. So let's take a look at how React in particular has made our lives a little bit better at Facebook. So we have a search product on our mobile site. And it's kind of been the same thing for a while, and we wanted to add some features a couple months ago. So we decided to use our best-of-breed web technologies, which right now is React, to rewrite the system and add these new features. And what the team found is that they were able to build more features in about the same amount of time it took to build the previous version. And they were learning React while they were doing this. And this is a really great benefit of having predictable code and fundamentally solid ideas underlying your architecture. And by the way, it performed about 50% better than the old version. So lots of great things fall out having predictable correctness and performance characteristics of your code. But it's not just helping us here at Facebook. It's also become a pretty great open source project for us as well. So a couple of years ago, we started building this at Facebook. Then we acquired Instagram. And Instagram's a great native mobile company, but there's not a lot of web expertise there. Facebook, on the other hand, has a lot of web expertise. So we wanted to build Instagram.com, which is a web experience for Instagram, and we wanted to use React. So in order to do that, we had to extract React out from the Facebook-specific use cases running on our big PHP platform and custom JavaScript packaging, and make it work on Instagram's Django stack that runs on Amazon EC2. It's very difficult for us to kind of reuse the underlying backend infrastructure at that time. But by the time we open sourced it to the world on GitHub, we had already dogfooded this with millions of people for many, many months, and we'd already figured out a lot of the kinks here. And today we've got a lot of great companies in the community using this. So a couple off the top of my head are Airbnb, Venmo, the New York Times. They're all pushing this to production. And a really great story is Khan Academy. They were one of our early users, and now an engineer at Khan Academy is, I think, our #2 contributor to React, which is really great. And you're going to be hearing about a lot more of our open source projects later in today, so keep that in mind. But it's not just open source. We're starting to bet big on React everywhere on the web. So our graph search product is powered by React. Our Page Insights product, which has a lot of high-performance data visualization, is also powered by React. And on our mobile side, I did mention our search system, but also uploading photos and navigation is powered by React. If you go to Instagram.com, the entire page is one big React component. And that includes basically all of the features. So I've talked a lot about how this has made our lives a lot better on the web, and I've talked about the browser DOM and JavaScript. But these are fundamental software architecture ideas. And we're starting to see these ideas appear in our native mobile apps as well. So our data layers are starting to move away from a traditional MVC observable system, and they're starting to present consistent snapshots of the entire data model at any point in time. And our UI toolkits are starting to resemble React. They're starting to be reactive components that present a completely declarative view of how the UI should look. And if you stick around for Scott Goodson's talk later, you're going to see even more influence and cross-pollination of ideas here. So I'd like to leave you with a quote from my favorite computer scientist, Dijkstra. He says, "Simplicity is prerequisite for reliability." We want to build better systems in less time. In order to do that, we need to predict what our systems are going to do. And you can't predict what you don't understand. So we need to make our systems simple enough to fit inside of our heads when we're working on a problem, so we can understand them, predict what they're going to do, and build higher quality software in less time. Thanks, everybody. We've got about 10 minutes left for questions, if anyone has anything.
Hello? Anyone hear me? All right, there we go.
I can hear you.
How do you guys handle routing in React?
Do you want to answer that? Or?
I mean, you can talk about what you do on Instagram.
Yeah, so we have like a much more kind of open source stack on Instagram, and we glue it into Backbone Router. The way that we generally model everything is in terms of this kind of the state that goes into your React components, and one of those components of state is the route. Another component of that state is your underlying data model. We don't really distinguish between route and underlying data model.
Hi, I was just wondering how long it took you to refactor all your code into Flux and React.
Yeah, so Pete did most of that. He did it in like a couple months. We've been using React internally for actually a really long time now. Jordan Walk is somewhere in the back, I think, and it was actually his idea. When he actually first presented this to me, he kind of came over to my desk. He's like, "Dude, I have this great idea." And I was like, "Listen, you're nuts. Like, this is never going to work, right?" And then he showed me some stuff, and it actually did work. So we started using it internally for a lot of internal tools and stuff like that. Shortly after we acquired Instagram, Pete was going to work with them and build out their web presence, and he really wanted to use this stuff. So I would say over the course of, 2 or 3 months, He basically divorced it completely from our Facebook build stack and kind of turned it into something that could very easily be put onto GitHub. So, and that was a team effort. It wasn't just Pete, but he was kind of the driving force. Yeah.
It's one of those things where we don't like rewriting code for the sake of rewriting code. So if there's a new feature, we'll generally try it out on that, and then it'll gradually kind of infect the rest of the system as we start fixing more bugs, that kind of thing. Yeah.
So I've used Angular. It looks quite similar. Can you compare and contrast your stuff versus Angular?
Versus Angular. So the question was comparing and contrasting React and Angular and Flux, and React plus Flux and Angular. They're fundamentally kind of, they do solve some of the same problems, but they go at it at very different ways. So React is focused a lot on treating your code as a black box. So there's no sort of observable abstraction inside of React. You simply say, hey, re-render the UI, and you present a consistent view of what you want your UI to look like. With Angular, you are basically passing data throughout these things called scopes, which observe your data model. And I think that that's a very leaky abstraction. It forces you to compose your application not in terms of functions and objects, but in terms of directives and model view controller and their flavor of model view controller. So while it does work for a certain class of applications, as you scale up, you start to miss the past 40 or 50 years of research into how to abstract a program. And so if you can kind of push that kind of data binding concern out to the edges of your system like React does, I think it leads to faster iteration time.
Hi there. How does it compare with Ajax, like jQuery, like where it pulls data and like sort of brings it into the page without like reloading the URL and stuff like that?
Yeah, I'm going to defer to Pete again on this one. There are actually two kind of different systems, but yeah, I mean, you can talk a little bit more.
So the question was, how does this sort of architecture compare to a traditional jQuery with Ajax kind of thing?
Right.
So Flux kind of manages your data flow, and your stores in that system will manage the Ajax calls for you. And you can actually do that. You can implement that with jQuery. You can implement that with parse. You can do basically anything that goes over the network you can implement and dump it into that architecture. So we kind of push that concern to a different system. And Flux is the integration point. As far as the comparison with jQuery, you can think of React as filling kind of a similar role as jQuery. So the idea of jQuery is like, you want to make some changes to the DOM and put the UI in a certain state. I like to think of React as the next step in that. So with jQuery, you have to think in terms of like, this is the initial state, this is the next state, this is the next state. With React, you only think of one state, and it's the current state.
Yeah, we've given various presentations about this too, and the thing that we kind of say is mutation is really hard. jQuery makes this really easy across browsers. It kind of smooths out all the inconsistencies, and it makes it so it's like very easy to manipulate the DOM and do things like that. But React tries to abstract it like a little bit further than that and say, look, if you didn't have to worry about mutations ever at all, and you just describe declaratively what your component and what your program looks like at any point in time, or what your views look like at any point in time, it actually allows you to kind of move a lot faster because you don't have to think about intermediary states. It's a little bit different of an approach. Yeah?
Do you have any public documentation or code or examples of anything of your Flux architecture besides what you guys kind of went through today?
I believe there's actually an example in the React examples directory for how to build like a to-do application with Flux and React. There's somebody who's preparing a blog post for the React blog to talk a little bit more about this.
Hopefully that'll be out in the next couple weeks.
Yeah.
All right, I think that's all we have time for, everybody. Thank you very much indeed. These guys are going to be hanging around at our open source table at the garage if you have any more conversations or discussions you want to have with them. But I'd like to finish off with a big round of applause for Tom, Pete, and Jing. And we will be back at 1:30 promptly to take a look at the server side of our web architectures.